Well, this is going to be recorded so everybody can see it later. So we'll just go ahead and work some problems that I think will be very important to you and helpful for the exam on chapters 1, 2, and 3. Okay, so first I want to share the review document key. Here it is. All right, so you should be able to see that. Let me make it a little bit bigger. Yeah, that should be, and let me make it just a hair bigger than that. Yeah, there we go. The reason I want to make it big is because YouTube, when they take my videos, they process them and make them available immediately. But they make them immediately available in low resolution format. So they're kind of fuzzy. And then they go through the process, which takes a lot more time, of generating a better resolution video file. And some of my files after a week are still processing. So my solution to that is to make things as large as possible and get the maximum resolution I can out of it in the beginning. Otherwise, the exam that pertains to that information is already come and gone, and you don't have the sufficient resolution to really get the impact of the video. Okay, so let's start. I got some marked off here on my hard copy, and I'll just go down and pick out the ones that I've selected. So this is going to be the format. Well, this is the review document. I don't know if you've looked for the review document, but in fact, let me get an answer from you. Have you accessed the review document for exam 1 yet?
No, sir.
Okay, let me show you where it is. So I need to stop this share, and I need to go back and share the, I think it's this one. Okay, so we're in the course. Start here. Go down to exam 1. This is where the exams are right here.
Mm-hmm.
But all the other material will be in lessons and reviews. And there's exam 1, all the materials that we've covered this semester, including videos. So there's chapter 1 lecture, chapter 2 here, and chapter 3 here, the one that I did when nobody was there.
Right.
And then the review documents are here in this folder. And if you go in here, you're going to see things here that are not visible to the student. These are grayed out, but this one, the review form will give you the review document with no answers in it, and the exam 1 review key will give you the answers. And then this document tells you how I worked each problem. It's in my handwriting, and I took great pains to make it legible. So with those 3 in hand, if you use those to review for the exam, you should be well prepared.
Okay.
And I'm going to share this one right here, the review key. So let me stop this share, and I go back to the other share that I was on just a second ago. Okay, so there's exam 1 review, chapters 1 through 3 in the key. So this gives you the answers. It doesn't tell you how I work the problem. You have to go look at that other document. But this video will help you with high points, really important subject matter as we use this as our guide for review. Now the exam's not going to be this long, right? This is excess. The reviews are always excess problems because, like I said before, your best friends in chemistry are curiosity and boredom. So if you work all these problems, by the end, you should be bored working these types of problems. And if you in fact you are bored, that means you know how to do it. Okay, so let's just take the first one. The number of milligrams in 6.6 kilograms. All right, so this is a unit conversion problem. So if we take 6.6 kilograms, you have two approaches here. You can use what you know about the relationship of the prefixes, kilogram versus milligram. So a kilogram is 1,000 grams, right? So that means this is 6.6 times 10 to the third grams, because 1,000 is 10 to the third. So multiply that times this, and you get the number of grams. A milligram is 1,000th of this one, which means there are 1,000 milligrams in a gram. Okay, so there's your multiplier, 1,000 times, because we went from grams to milligrams. But you combine these two and you get 10 to the sixth, right? Exponents, if you multiply two numbers of the same base with exponents, you just add the exponents. So that's the answer, 6.6 times 10 to the sixth milligrams, which is B. Now that's one way to work the problem. I'm going to show you another way. And this way, let me do that better. Kilogram. Okay. This way we use dimensional analysis. Remember when I talked about conversion factors and why conversion factors work? Because every conversion factor is equal to 1. It's a ratio of one number to the other, and the ratio resolves to the number 1. So what's the relationship? Well, here's where we want to end up. Milligrams. We're going from kilograms to milligrams. But suppose I don't know a direct conversion between this one and that one. But I do know that for every kilogram, there are 1,000 grams. Right? And now why did I do it that way? Because any whole number any number sitting by itself is understood to be in the numerator. Right? And so are units of measure. So that's 6.6 kilograms over 1. So if we put kilograms in the denominator here, it's going to cancel. Right? So that cancels and leaves us with grams. We just have to be sure that that is equal to 1. And how do we know it's equal to 1? Because 1 kilogram equals 10 to the third grams. That's where we get this conversion factor. If that's equal to that, then this ratio is equal to 1. Okay, so we've got to grams, but we're not to milligrams yet. So we'll do a chained conversion. Now we've got grams here, we need to cancel. And what's the relationship to give us milligrams here? Because that's in the numerator and that's in the numerator. Well, the relationship is 1 gram is 10 to the third milligrams. Or this would work just as well. 1 milligram is a milligram, or 10 to the minus third grams. Okay, either way works fine. All you have to do is remember your mathematics and what to do with the numbers. Once you've done all your thinking and you start to crunch numbers, be sure you crunch them correctly. Okay, now we know that we've got the right units. Now it's just a matter of resolving the numbers. Right? So we've got 6.6 in the numerator, and we've got 10 to the third in the numerator, but this one's in the denominator, right? So what do you do? How do you combine this one and this one? Well, they don't cancel because they're different powers, right? But if you take a denominator powered number and put it in the numerator, what happens to the power? Changes sign. So 10 to the minus third now is 10 to the third in the numerator. Now we can add these together. And there's your answer. Okay, that was a long way around the barn, but the quick way works okay, but this way has much broader application. This dimensional analysis works in numerous problem-solving situations. Whereas the prefix mode that I used earlier only works when you have related prefixes. Okay?
Mm-hmm.
All right. So that's number one. And I'm going to make a little note here so I don't go back and try to do it again. I have a habit of doing that, don't I? Okay, so how about number two? Water has a density of 1 gram per milliliter. So that's how the mass of water per milliliter is 1 gram. That's an intensity factor. In other words, it doesn't matter how much water you have, this value for water is always the same. You can have a little bit, you can have a whole lot, it's still 1 gram per milliliter. So, which of these objects, object 1, 2, or 3, will float in water? So there's your question. We want to find out which one floats. That's the question. What do we need to know to determine if something will float? We need to know the density of the liquid that you put the object into, right? And then we need to compare the density of the object to the density of the liquid, right? Because anything that's more dense than the liquid will sink. Anything that's less dense than the liquid will float, right? So most people are less dense than water, right? Because you float. I've heard of some people that can't float, so they must be more dense than water, right? Oh, we got another attendee. So let me make note of that. Give that person credit for showing up. So what we need to know is the density of these objects and compare them to the density of water. So anything that's less than 1 will float. Now, the temptation here is to go through the laborious process of calculating the density of each of these objects and getting an actual number. But we're in the middle of a test and we're got to move fast. So if you look at the problem, you see that all you need to know is the ratio of mass to volume greater than 1 or less than 1, or even equal to 1. Right? We don't need to know the exact value. We just need to know what's the ratio. Is it on this side greater than, or is it on this side less than? So all we need to do is just say, okay, object 1, 2, 3. Object 1 would be 50 grams and 69.4 milliliters. 50 grams and 69.4 milliliters. That's equal to density, right? Mass divided by volume. So what's that number? Is that going to be greater than 1 or less than 1? It's less than 1, right? It's less than 1, so it floats. Don't even have to do the calculation. How about the next one? 60.9 grams and 54.7. How's that one? Is that one less than 1 or greater than 1? It's greater than 1. The numerator is bigger than the denominator. That sinks. And how about 3? 100 divided by 40. That's greater than 1. That one sinks. So the only one that floats is 1. That's why the answer to this one is B. Right? And that took a whole lot less time than actually doing the calculations. In fact, you don't even have to write it up here. You just say the ratio in your mind is 50 to 69. 50 divided by 69, less than 1. 60 divided by 50, less than 1. 100 divided by 40, greater than 1. This one's greater than 1. And you got your answer in 15 seconds. But the key to this problem is knowing what the question means. What the question means is, what's the density of the object relative to the liquid? All right, so you have to understand what the question is asking for. Okay, let's see. Yeah, let's do number 3 as well. And then we'll go further down the line. Because this is a simple conversion. Actually, it's not so simple because you have a negative temperature that you're trying to convert to from Celsius to Fahrenheit, minus 12.2. And we want to know Fahrenheit. Okay, so what's the formula? Well, at the end of every review document is useful information. So let's go down here and I'll show it to you. Here it is, useful information. If the useful information is at the end of the review document, it will be available for the exam. Now, I'm unclear, when you go into Respondus Monitor Lockdown Browser, I'm unclear whether it'll shut you out of accessing that document from within Blackboard. So it might be a good idea to first go into Blackboard. And you know what? I'm going to do that right now. I want to answer that question for myself. I want to see, so I'm going to unshare. I'm going to stop the share for a second. And I'm going to go back into Blackboard like I was before. Let's see, where was I? Blackboard. Here. Okay. Yeah. Okay, so let's go back out to the exam folder, because that's where I want to put that information for you. Not far enough, sorry. Lessons and reviews, nope. Back out here. Now, come back down to exams. Here we go. Exam 1. There's useful information, right? It's legal for you to have that available while you're working the test. Now, as insurance, the first time you do this, I would suggest that you open this up in Blackboard before you use the lockdown browser. Just go in here like you normally go to the course and print that. Okay, it's a one-page document. Print that document. Then when you go into lockdown browser, you'll guaranteed to have it. And then when you go into lockdown the first time and go into this exam area through lockdown browser, it's just like any browser, and you call up Blackboard. Right? Then see if it's available for you that first time. If it is, then every test beyond that, you won't have to print it out unless you want to ahead of time. Then it'll be there for you in the lockdown browser. Okay, does that make sense? Because everyone will have useful information. And the useful information is extracted from the review document. If you see the useful information in the review document, it could be just like that little table. It would be that, and sometimes I add other stuff that we've covered in that chapter that you will need, like a periodic table, right? In exam 2, there's probably a periodic table there too. So you may have more than one document. Or if you choose to print out the useful, review document, then you'll already have the useful information on the last pages of the review document, right? So you'll have it there, and you can use those pages. I just don't want you looking at the rest of the review document while you're taking the test. So, and the respondents monitor will be looking at you anyway, so it'll see if you're not completely kosher in your behavior. Okay, so let me stop this share and go back. So we're going to reshare the, there we go. So that's what you'll see in that first useful information document. Let's go back up and pick up number 3. There we go. Okay, so we want to find out what's the temperature in degrees Fahrenheit if we know it's degrees centigrade. Well, you need that formula, right? And I have the formula memorized like this. Okay, degrees Celsius times that plus that equals Fahrenheit. So this formula, the way it's written, is just what we need because the unknown is out here by itself. So we don't have to do any transformations. We don't have to do any algebraic manipulations after we plug the numbers in. So we just need 9/5 times minus 12.2 plus 32. Now remember when we talked about significant figures, these numbers are exact numbers. They have infinite significant figures. These have infinite significant figures. So all we have to be concerned with is this one, right? So 9/5 times that one is going to have 3 significant figures in it. And if I get the calculator out, in fact, it doesn't matter. You don't have to use the add subtract rules because we've only got this number and our answer can have 3 significant figures in it. So it's 12.2, change the sign, and 9 times 5 divided. Now, the formula may also say 1.8 here. But if you divide 5 into 9, I guarantee you'll get 1.8. And that's minus 21.96 from my calculator, plus 32, right? So you have to be conscious of the sign. That's why this problem was created, because that's a negative sign. And if you're not careful, you could make an error in your calculation. So now we get 10.04 degrees Fahrenheit, but we can only keep 3, right? So we round it off, and that goes away because it's less than 5. and our answer should be 10.0, which it is. E is the answer in this one, 10.0 degrees Fahrenheit.
Do you care if we use a calculator on the exam?
No, you can bring a calculator. And just in case, if your calculator battery dies or if your calculator fails on you, I've enabled a scientific calculator in the browser. So if you look at the top, once you open the lockdown browser, if you look at the top, you should see a little calculator icon. So you have that access in case there's something goes wrong with your calculator.
Thank you.
Okay, so now let's skip to number 7. Let's see. This, number 7. Here we go. So here we go the other direction. We want to convert 232.0 degrees Fahrenheit, and we want to convert that to degrees centigrade. So using the same formula, we can either plug this number in here and then do the algebra, or we can solve the equation for our unknown and then plug the numbers in. Right? So if we put the number in here, that means we have to subtract this from both sides, right? So it'll be minus 32 over here, and that means we're starting with 200.0, and then 9/5 on this side is 5/9 on the other side, right? You flip it when you go across the equal sign. So 5 times 200 is 1,000 divided by 9. So what's 1,000 divided by 9? It's less than 10. So rather than 100, it should be greater than 100. So I can estimate if I'm in a hurry, and I can say it's probably C. But if we do it the other way, solve this for C first. So that means F minus 32 equals 9/5 C. And then C equals 5/9 times F minus 32. Like that. Then you plug in the numbers. Okay? And in fact, the answer is C. Now, if I'd been really sneaky and I put in 111.1 as a possible choice, and I put in 112.1 as a possible choice, then you would have to do the calculation to differentiate between those two, because estimating won't get you there. But in this case, they're so far apart, estimating gives me the answer. All right, that's number 7. So let's see, what's the next one I checked off? Oh, number 12. So we go down to 12. Here we go. So what's the question number 12? In the sum, 54.34 plus 45.66, the number of significant figures is. All right, this requires you to remember the add subtract rules and significant figures. So the temptation, and students do this all the time, the temptation is to say, okay, they both have 4 significant figures, so the answer must have 4 significant figures. But that's the multiply divide rule. The add subtract rule is different. 54.34 and 45.66 requires that you line up the decimals, correct? Then you add. 0, carry the 1. 0, carry the 1. 0, carry the 1. There. Okay? So, how many numbers can we keep? Well, we keep the least number of significant figures. So they're both equal, so we can keep all of them, can't we? We keep all of these. That means we have 5 significant figures in the answer, not 4. So that's why the answer is D. I picked that one out just to show you that if you get in a hurry and you forget the rules or you misapply the rules, then you get it wrong.
Say if it was like 100.01, would it be 4 significant figures?
No. Because the add subtract rules that said the number of decimal places you keep is dependent upon what you start with. So we've got 2 decimal places for one, 2 for the other. You can keep both of them, even in the answer. So that 0.01 stays. You don't round it.
Okay.
Okay? And you don't get rid of any significant figures that you're permitted to have. Okay. Let's go down to 15. This is a reasoning question. Which of the following is an element? So we have alcohol, salt, helium. And let's see, there are 2 more, aren't there? Sugar and vinegar. Okay, which of the following is an element? Well, this is fairly simple, right? Can you find these on the periodic chart, periodic table? Well, if you've already started, I hope you have already started to memorize the elements, then you should recognize that alcohol is not an element on the periodic table. There's no symbol for it. There's no symbol for salt. There is for helium, right? So we know that one is. Sugar. There's no place on the periodic table for sugar. There's nowhere for vinegar either. So helium is your answer. It's an element. None of the others are elements. Alcohol is a compound. Salt is a compound. Sugar is a compound. Vinegar's not a pure compound. Vinegar is a mixture, a solution of acetic acid and water. In fact, it's 5% acetic acid and water is vinegar. Now, you don't know what acetic acid is yet, but you will. We're going to cover that. All right. So that was 15. Let me mark that one off and see the next one that I've checked. Let me put this, stick this out of the way. There we go. 18. I want to take a look at 18. Now, as always, if you've already gone through these and worked some of these problems and they've given you trouble, by all means, stop me and let's work the ones that are giving you problems first so that we don't run out of time. Okay. So, and you can do that anytime. If you don't think of one right now, but you think of one later and we're still in session, then just stop me and we'll tackle your problem first. Or whenever you think of it, of course. 18, okay. How many liters are in a 29-ounce bottle of pop? Okay, 18. So we've got 29 ounce. Yeah. 29-ounce volume. And we want to convert it to liters. Okay. So I like to write the pertinent information up on the board or on my paper separate from the problem, because word problems and questions like this, they're inherently confusing. The purpose of a word problem is to confuse anyone who doesn't really know the subject matter. So in order to determine if you know it, it's always a good idea to take the information that's given and slap it up on the board away from the problem so you can see the information that you have and the question that's being asked. Okay? Now, what else are we given? Well, we're given conversion factors. 1 quart equals 32 fluid ounces. Now, maybe we don't need all of this information, but I'm putting it up here so it's, and simply by writing it, sort of ingrains it in your short-term memory. 1 liter equals what? 1.0567 quarts. Okay, those are the conversion factors. Now, let's set up the conversion. This is the dimensional analysis problem. We're going from units to units. 29 ounces is where we're starting. And we want to end up with liters. Okay? So that means if it's a one-step problem, that means we need a conversion factor that will go from ounces to liters. But we don't have one. Ounces to quarts, quarts to liters. So what we have is a chained conversion. We need more than one conversion factor to get there. So what do I want to do first? Well, there's liters. So that one is going to give me this over here. But how do I get from these units, right, liters and quarts, from here to there? Well, this, analyze the dimensions. Liters on top, that's good. Quarts on the bottom, that means we had to cancel quarts over here. If it's on the bottom there, it's got to be on the top here. So what do we have? Quarts, ounces on the bottom. So that works. Ounces cancel, quarts cancel, liters are left over. We just need the numbers. So for quarts and ounces, we have 32 here and 1 there. And for liters and quarts, we have 1.0567 quarts and 1 liter. So there we have canceled this one, this one, this one, this one, leaves us that one. Now, that's the thinking part. That's the hard part. The rest is crunching numbers. Now, crunching numbers can give you the wrong answer if you don't do it right. So this is in the numerator. These are in the denominator. So we say this one times that one times that one, which is the same number, 29, right? Divided by this one. And then divide that answer by this one. And I get, well, let's see, let me write everything that the calculator gives me. Well, almost everything, because it strings it out. 0.857623 liters. Now, how many of those can we keep? That's an exact number. All conversion factors are exact. That's an exact number because it's a conversion factor. This is the only limiting factor in the whole sequence. And these are all multiply, divide problems. So we just look for, we go all the way to the end with our answer, and then we look back to the limitations on the first, where we started. 2 significant figures means we look here, right there. That one's 7, so this one has to come up to 6. 0.86 liters. Then we look and see, is that answer there? There it is right there. B, 0.86. Okay? It looks like it's very complicated. And some problems are, I admit, they're very complex. So the key to working complex problems is to first find out what the question is. Then to get the information that's delivered by the problem up and away from the problem, the statement of the problem. Then you say, how do I get to the answer of that question? Can I go directly there, or do I need to go several places? If it's very complex, you may have to devise a sequence of operations. And very often, those sequences are best developed by going backwards. This is what the answer needs to be. How do I get there from there? Well, I got to know this before I can go there. But to get this one, I got to go back over here and get that one. Right? So working backwards is usually the best policy for answering a complex problem. This one looks complicated, but it's really not. You just have to be methodical, very methodical, and that requires that you work lots of these types of problems so that when you see one, it doesn't freak you out. It looks familiar. It's an old friend that you're bored with, and you just go in and knock, knock, knock. We're done. Okay, so that was, what was that? 18. 18. Next one I want to do is 20. Which of the following is a homogeneous mixture? I'm not even going to put this one on the board. We're just going to look at the problem and approach it rationally. What's the question? Which of these is a homogeneous mixture? That's obvious. I mean, it's actually, there's very little blue smoke in this one. But to answer the question, it's best to go backwards. Which of these are mixtures? Because if they're not mixtures, then the modifier homogeneous doesn't matter. So, mixture. Is gasoline a mixture? As a matter of fact, it is. It's a mixture of octane and various other additives that are supposed to keep your engine clean and make it burn better. So that one qualifies as a mixture. Copper metal, is that a mixture? No, that's a pure element. So we throw that one out. Jelly beans, is that a mixture? Oh yeah, lots of different colors. Keep that one. Pure water, is that a mixture? No, it's a pure compound. All right, so throw that one out. Can't be a mixture. Soil, is that a mixture? Take my word, soil is a mixture. Lots of different things. It has both mineral components and organic components. It has different particle sizes. A more complex mixture I can't imagine than soil. So we get to keep gasoline, jelly beans, and soil. Now, which one's homogeneous? Now we apply the modifier. What is a homogeneous mixture? There's another name for it. A homogeneous mixture is a solution. And a solution is characterized by uniform composition. Anywhere you look in that mixture, if it's a solution, if it's homogeneous, anywhere you look will have the same ratio of components. Everywhere, exactly the same. Gasoline qualifies. That is homogeneous. Jelly beans, we know, don't qualify. They're heterogeneous. Take 2 handfuls, you have a different mix of colors. Soil, take my word for it, it's as heterogeneous as you can possibly get. If you've ever stuck a shovel in the ground and pulled it up and looked at where the shovel came from, you'll see stratification in the soil, right? Different layers. That should be a tip-off right there that is heterogeneous. So the answer is A for 20. Let's look at number 22. Oops, sorry. There, 22. A graduated cylinder contains 20 milliliters of water, 20.0 milliliters of water. Sometimes it's helpful to draw a picture, right? So let's draw a picture. Graduated cylinder. It contains 20.0 milliliters of water. So let's say it's a 50 milliliter graduated cylinder. 20 will be about right here. That's 20.0 milliliters of water. Okay, we take an irregularly shaped object, place it in the cylinder, and the water level rises to 31.2 milliliters. So it rises up here to about here, 31.2 milliliters with your object in the bottom. Okay, so that one is where it was, is not there anymore. If the object has a mass of 80.4 grams, what's the question? Density. What is the density? Okay. So what do we need to know to do density? Density equals mass divided by volume. Do we have the mass? Yep, right there. Do we have the volume? Well, sort of. We have the information we need to find the volume, right? Why did the water go from 20 to 31.2? Because we dropped an object in there. So the displacement from here to here is the volume of that object. So 31.2 minus 20.0 is the volume of the object. Is that right? Yep. And our decimal place is here for both of them, so we get to keep that too. So 11.2 is the volume. So now we have D equals 80.4 grams divided by 11.2 milliliters. Okay, that's the thinking part of the problem. The rest is number crunching. So I've got 7.1786. Grams per milliliter, right? That's too many significant figures, right? We can't legally keep all of them. But the answers, both of these, now we're in multiply divide mode. Rules for multiply divide say they're both the same, 3 significant figures, so we can keep 3 out over here. So right there, we look to this side, that's 8. So that means this 7 becomes 8, and these go away. 7.18 grams per milliliter. And that's why the answer is A. All right, next one I want is 25. Here we go. Okay, what Kelvin temperature reading equals 61.2 degrees Fahrenheit? So what are we given? 61.2 degrees Fahrenheit. And the question is, what is that in Kelvin? Do we have a direct path to Kelvin from Fahrenheit? The answer is no. We don't have a formula that we've learned to go from one to the other. Now, we could derive one, and I'm not going to bore you with that. I think it's more instructive to see this as a multi-step problem. Right? So what do we know about Kelvin? We know that if we have the Celsius temperature, we can calculate Kelvin, right? Right. Kelvin equals degrees C plus 273. And that should also be in your useful information. Right. So now what we need is degree C. We do have a conversion for this one to that one. Okay, that's just the one I remember. So if we take this one, put it over here, and then resolve, solve it for the unknown, okay? So that means this subtracted from that is what? That's 29.2. Remember, this is an exact number, that's an exact number. So we can keep all three of these significant figures. So minus 32 here would be 2, 9, 3 and 5 is 2. 29.2. Well, let's just leave the math just like it is. 9/5 C. Now to solve for C, we say 5 times this divided by 9, right? We're crossing the equal mark. So this quotient flips over. So 5 times that divided by 9 is what? I get 16.2, right? So C equals 16.2 degrees centigrade. Yeah, that's reasonable. So now we take this one and plug it in here. And that's an exact number. So we can keep the decimal place. So K equals, let's see, 273. 289.2. K. Not degrees K, just K. Let's see, do we have that one? Oh, 289.4. Why did we get that? Okay, I have an explanation. 273.15, what would that do? If we used a different value, see, I've truncated this number to 273 because that's typically what we use in this class. But if the authors that devised this question said that it's 16.2 and then 273.15, then we get 289.35. Rounded up to one decimal place, because that's all we can keep, then we have 289.4. Okay, so here's a valuable lesson in test-taking technique. If you've got multiple choice answers and they're all unique, right? You don't have anything here that says all of the above, none of the above, A, B only, or C and D only, or something like that, or some alternate choice. Then you look and you find the best answer. The answer that's closest to the one you got is 289.4. That's the one you pick. Okay? If the question were fill in the blank, right, do the calculation and put your answer in, then I, as the instructor, the system would not be able to grade that problem. So I, as the instructor, would have to go in and say, okay, yeah, that's right, right? I may have been expecting 289.2, but 289.4 says you know what you're doing. So you get credit, right? Because you worked it just a little bit different than I would have, but it's not wrong. So there's another teaching moment. What's the difference between 289.4 and 289.2? Error, right? Calculation error, possibly. So we had a instruction on error as well, didn't we? Okay, I got another attendee. Let's see here. Okay, here we go. All right. Okay, so that was 25. 26. Which of the following processes is a chemical change? Okay. It's good to know what we mean by chemical change. Right? Chemical change requires that the product has a different identity than the reactant, or the products, at least one of them, has a different identity than the reactants. Okay, and how does that happen? Well, it happens because bonds have to be broken. If you just change the phase, like melt ice or boil water, you haven't broken any bonds of the molecule of water. The water still has its identity. So we look for changes, any of these that have changes that reference breaking of bonds, changing of identity. So let's see, dry ice sublimes when left on the table. Have we changed it from carbon dioxide solid to carbon dioxide gas? No, it's still carbon dioxide. So A is a physical change. How about the light on a candle burns until a bell jar is placed over it for a period of time? The chemical change is the candle burning. Yes, we've gone from wax and oxygen in the bell jar to carbon dioxide and water. We've changed identities of the products. Now, why does it matter that we put a bell jar over it? Well, we've starved it of oxygen. So the reaction runs until the oxygen goes out and then it quits. So really, you don't need to know the bell jar part. The chemical change is here with the burning of the candle. How about C? Just for the reason we need to do C and D is because none of the above processes are chemical change. Well, actually, E's false now because we know that one of them is. So that means test taking technique, B's the answer. A few drops of red food coloring is added to a beaker of hot water. Water turns red. We didn't change any identity. We just mixed two things together. Liquid nitrogen dumped on the floor vaporizes. That's pretty cool too, to watch it. In fact, you can put liquid nitrogen in your hand, and as long as you keep moving it, right, it won't burn you. And then to get rid of it, you just slap it on your pants. But if you let it sit, it'll eventually burn your hand. So why does it not burn your hand if you keep it moving? Well, you're introducing fresh tissue all around there that's at body temperature. And wherever it's been before, it was cool, starting to cool, but you moved it to a new location. Plus, liquid nitrogen boils at a minus 195 degrees Celsius. And the temperature difference between your hand and the nitrogen is huge. So energy is sufficient from your hand to vaporize the liquid nitrogen on the surface of your hand. And what you get is this liquid nitrogen actually forming a layer of nitrogen gas underneath the liquid nitrogen. And gas does not conduct heat as efficiently as the liquid does. So you form an insulating layer. There's a German word for that. It's called Leidenfrost. You can see it if you heat up a pan on your stove, like a cast iron skillet. You heat it up with nothing in it, and then you throw a little water in there. And what does it do? That bead of water just bounces around because when it hits that hot pan, the surface of it vaporizes instantly, and it kicks the water droplet up. That's the Leidenfrost effect. Okay, 26. We got our answer is B. Now let's see. I'm going to go to 30. How are we doing on time? 10 o'clock? Okay, we're good. I got over an hour and a half left. 30. Next page. Here we go. This is a test of whether you is understanding what the prefixes mean, right? We have fundamental units, and then we have derived units that require a prefix to modify the fundamental unit. So it doesn't matter what the fundamental unit is until you actually use it. Beforehand, you need to know what the prefix means so that you get the size unit that you want. So which of these is used to designate 1/10 of the fundamental unit? And you just have to know. You have to memorize it. So what's big M? Big M is mega. So the fundamental unit is modified by 10 to the 6th power, multiplied. K is kilo, 10 to the 3rd, 1,000 times. C, centi, which means 1/10. No, 100. Excuse me. Brain fart. C means 100th. M means 1,000th, 10 to the minus 3rd. D is deci. Deci means 1/10. So that's your answer, E. Let's see. 36 is my next stopping point. Here we go. So this is it. This question is in the form of a statement, and the answer is A, B, C, D, or E. The volume in milliliters occupied by 41.9 grams of mercury is. Okay. $36. So what's the question? We want to know how many milliliters of mercury we got. Right? Milliliters of mercury. What's the information that we're given? We're given the mass of the mercury, 41.9 grams. And we're given the density. Let's see, do we even need the density? Now, just because it's there doesn't mean we need it. As a matter of fact, we do need it. This is a density problem. This value is equal to mass divided by volume. So there's your mass. There's your density. We've got an equation in one unknown. We can solve it for volume, and the units of measure will be milliliters because it's right there. Okay? So we could solve that, say volume on this side leaves mass on that side divided by density on this side. So the mass is 41.9 grams divided by 13.6 grams per milliliter. Okay, so is that going to give us the right units? This is a good habit to get into. Check your units. See, once you've set up your calculation, are you going to get the right units of measure to answer the problem? Right? We need milliliters. Is this going to give us milliliters? Well, look, we've got a numerator, we've got a quotient in the denominator. So when we do the calculation, everything has to come into the numerator. to complete the calculation. So what happens to this quotient? Well, when it comes into the numerator, it flips up, right? Because the numerator in the denominator is the denominator. The denominator in the denominator is a numerator. So that's milliliters times grams divided by grams. Grams cancel, leaves us with milliliters. So we have the right units, we know. We just need to do the calculation. So 13 into 40 is about, well, it's 3 point something, I think. Let's see. Yeah, it's a little over 3. So which one's a little over 3? A. I could have used my calculator, sure. And like I said before, if another choice was very close to that one, I would have to do the calculation. But since, well, okay, I take that back. Since one of the answers is none of these, you do need to do the calculation to verify that it's the correct one. So 13.6 into 41.9, both of them have 3 significant figures. So you can keep 3, do the division, and your answer will be 3.08 after you round it off. And that means E is false, because there is an answer up there. Okay, 40. How many significant figures are in this number? All right, so we need to remember our rules, don't we? 40. This one's getting a little weak. Let me switch to a fresh marker. So 0.004009. Oh, and this is, what did I say, 40? Okay. We're not concerned with units of measure here. We just want to know how many significant figures are in that number. So we've got a bunch of zeros in there, right? So we've got to apply the zero rules. So which ones are significant? Well, which ones are not significant? Those are not significant. These are bracketed by 2 non-zero numbers. They're significant. This one's a 0 to the right, and there's a decimal. That one's also significant. So we have 1, 2, 3, 4, 5. 5 significant figures in that number. There you go. There's the answer, E. Another way to approach it, write it in scientific notation. 1, 2, 3. Five significant figures. Okay? This brings up another pet peeve of mine. I don't know where students learn this habit, but you need to get out of it. Whenever you have a decimal sitting out here to the left of a number, that's wrong. When you have a decimal fraction sitting like that, it has to be bracketed like that. That 0 is not significant, but it's important. It identifies that as the decimal point in the number. If you stick it out there all by itself, it's too easy to get it confused with some other parts of the problem or the statement or whatever else. Don't leave a decimal hanging out there. That's an orphan decimal. And I don't like orphan decimals. So that's 40. 41. Okay. What's the SI prefix that corresponds to a factor of 10 to the minus 2? So what does 10 to the minus 2 mean? 10 to the minus 2 is the power equivalent of 1 divided by 100. 100th is 10 to the minus 2. So the prefix for 100th is centi. Okay? Let's see here. I want to go to 47 next. There it is. So we have this calculation, and we want to know how many significant figures are in the answer. So you're going to have to do the calculation, and you need to use your rules. 47. So that's parentheses first, right? So we've got parentheses here that tell us which ones to do first. And rather than write that number up there, let's just look at the problem. So which is in parentheses? Well, this first part here is in parentheses, but there's no calculation to be done. This one's in parentheses, but there are no calculations. This one's in parentheses, and we do have to do a calculation. We have to use the add subtract rules for this part of the calculation. So let's do that first. 33.12 and minus 31.12. And those are degrees centigrade. Subtract. So 2 from that is 0. 1 from that is 0. 1 from that is 2. And 3 from that is 0. So we've got nothing out here. That means we only have 3 significant figures left for that calculation. Okay. Now we can say this one times that one times that one will give us our next step. So 2 times 0.4333 and then times 412.1. So multiply those 3 together. We know what? We don't even have to finish it. You know why? Now we're in the multiply divide rules, and all we have to do is know which is the least number of significant figures. There's 4, there's 4, there's 3. Right? So 3 is all we can keep in the answer. We don't need to know what the answer is. The question is how many significant figures? And B is 3. Okay, save yourself some time. All right, so that's 47. I want to look at 48 next. Which is an example of a homogeneous mixture? All right, we've done a homogeneous mixture before, but it was a different set. We have to find out which ones are mixtures first, right? So soil or dust, I don't know why they put that in there. Sodium chloride is not a mixture. It's a compound. It's pure substance. Aluminum is an element. It's pure, not a mixture. Vodka is a mixture, right? All booze is a mixture. It's got water and alcohol and other stuff. Oily water, that's a mixture. I mean, if you mix it up. So we can choose between E, D, and A. We already know that soil, even in the form of dust, is not homogeneous. It's heterogeneous. Oily water doesn't mix very well, so even if you mix it really good, like you're making your own salad dressing, right? Oil, vinegar, seasoning. I like to use Mrs. Dash. It's simple. You put it in your container and just shake the hell out of it and then dump it on your salad before it separates. Well, it immediately starts to separate. So it's heterogeneous. The only one that's homogeneous is vodka, right? Water and alcohol. Got a visitor here. Okay, so D's the answer. Vodka is the only one that's a homogeneous mixture. Excuse me. Let's see, what's the next one I'm marked? 68. Let's see what 68 has to say about the world. There we go. And one more page. There we go. I don't even have to write this one up. 68. You just need to know this one. A cubic centimeter is equivalent to what other metric volume unit? It's equal to a milliliter. Milliliters, cubic centimeters are equal in size. So if you see something old is sitting on the shelf and in a medical environment, and you see it says like so many cc's, that's cubic centimeter, you know immediately that's 100, or that's the volume is in milliliters also. Uh, 71, how about that one? The state of matter for an object that has a definite volume, but not a definite shape. Right, so you think about it. What's a solid? Definite volume, definite shape, right? It doesn't need a vessel. Next one, liquid. Change from solid to liquid. Definite volume still, but not a definite shape. There's your answer. Because if you go to gas, that's not a definite volume and not a definite shape. So liquid has to be the answer. That's why it's E. Uh, 84. 84. Here we go. 84 is going to need us to look at this beaker. So let's look. The beaker's got a liquid in it, it appears. And it's got markings on the side, 10 milliliters, 20 milliliters, 30. Okay. And we want to say, well, okay, now let's look at the problem. The question is, what is the new volume of water in the beaker? So they're probably going to add some to it or take some away. You take 20 milliliters of water, 20.0 milliliters of water from a graduated cylinder, and add it to the beaker of water below. What's the new volume, right? This requires that you understand that it's going to give you a higher volume, of course, but you're using two devices to measure your volume. What's the limitation on your answer? The least accurate measure is the limitation. 20.0 milliliters says that it came from a graduated cylinder that was accurate to 0.1 milliliters, 20.0. Whereas this one is only accurate to actually tens of milliliters. So what are we saying we have here? Well, it looks like we have 15, right? So 15 plus 20 is 35, but we can only keep two significant figures because this is 15. So 15 and 20 is 35. That's why 35 is the answer and not 35.0. Okay? Everybody follow me on that one? We're limited by the least accurate device. Excuse me. Let's skip over to 94. I'm going to use the scroll bar for this one. There we go. Which of the following is only a physical change? So one problem before, we were looking for chemical change. Now we're looking for physical change only. And we see down here, test taking technique, at least two of the above exhibit only physical change. So that means that we've got to go through all of them and be sure that there's only one, or if there are two, then E would be the answer. So let's look. Leaves turn color in the fall. Is that a physical change? Well, actually, the change of color in this case is an indicator of chemical change, because the leaves are starting to deteriorate. B, a banana ripens. When a banana ripens, it gives off a gas that wasn't there before. And it has changed its identity. So anything that starts to rot is a chemical change. Cookies burn in the oven. Oh yeah, we're carbonizing the ingredients of our cookie into char. That's a chemical change. Sugar dissolves in coffee. Okay, there you go. There's the clue. Sugar in your coffee is still sweet. It's still sugar. It's just changed from a solid into a solution of whatever's in the coffee plus the sugar. So D is the only answer here that is a physical change. The others are chemical changes. All right. Let's see. We'll move along to 107. So let's look at 107. Here we go. Fill in the blank. Okay. So a blank is a summary of observed behavior, and a blank is an explanation of behavior. Okay, remember when I was describing the progression of scientific discovery over the decades and centuries? We generally come to laws first. And laws just say what happens. If these are the circumstances, if these are the input data, then this is the output data. It's like a black box. Goes in here and comes out there. I don't know what happened in between. I don't know why it happened. It's just an explanation of an observed behavior. So that would probably be a law, a summary of observed behavior. Right? It can be a mathematical formula, or it can just be a statement, right? Like Newton's first law of motion. An object in motion tends to remain in motion unless acted upon by an external force, and an object at rest tends to remain at rest unless acted upon by an external force. That's a statement, but it's just a law. It doesn't say why. It says tends to. Here in the second part is an explanation of behavior, an explanation of why something happens. That's a theory. An explanation here means why does it happen? So the answer is B. First one is a law, second one is a theory. Okay. 114 next. Here it comes. So your friend is 5 feet, 9.8 inches tall. How tall is your friend in meters? Right. This is a multi-step problem. So we need to break it down. What are we given first? Let's do that. 5 feet and 9.8 inches. And we want to end up with meters. Okay? Now, can we convert 5 feet 8 inches directly into meters? No. In the first place, we have 2 different units of measure. We can't directly convert 2 different units of measure into a final answer. What we could do is convert feet into meters and inches into meters and add them together. And that would be the total in meters. Or we can convert one of these into the other one and get 1 unit of measure. Then we can go through a dimensional analysis to meters. And that would be my choice. So let's convert feet into inches first. So 5 feet times 12 inches per foot equals what? Equals 60 inches. Now, why did I do that? Because 60 is the answer, 5 times 12 is 60. But that has two significant figures, and I want to be sure that we keep those. So that's why I put that decimal there next to the 0. Otherwise, it's only got one significant figure, right? So I put the period there. 60 inches. Now we add 9.8. 9.8 inches is 69.8 inches. Now, we would have to round that off to 70, wouldn't we? 70 inches. Because we can only keep that decimal place up here. Now we can convert inches to meters. So if we're coming backwards, and we want to go to meters, well, inches is a lot smaller than a meter. So our first conversion is going to give us a small unit, and we want to go to meters from the, we're going to take this to metric system, and then we're going to adjust the size of the unit to the metric meter. So the one conversion factor I do know is centimeters. 1 inch is 2.54 centimeters. Now that I've got centimeters, I can convert it to meters. How many centimeters in a meter? Well, centi means 1/100th of, so it takes 100 of them to make 1 meter. Okay, there we go. So now we've done all the thinking. And you check your units. Those cancel, leaves you with meters. That's good. And then you do the calculation. 70 times 2.54 divided by 100 equals what? Well, it equals 1.8 meters. And 1.8 meters means that we're limited to this, 2 significant figures. Okay? Notice that one of the answers here was 70 meters from here. If you stop there and think that that's meters, then you're going to pick A and be wrong, of course. That was 114. I find if I erase the black pretty soon after I write it up there, it comes off okay. If you leave black up there for half hour, it's kind of hard to get it off. 116. Let's see what 116 is all about. Which of the following is incorrect description? Which of these words don't go together? Right? So we've got unique answers, A through E, so only one of them can be right. Which is the incorrect one? A homogeneous mixture. Is that possible? Well, yeah. Mixtures can be heterogeneous or homogeneous, so that's true. A solid element, right? Yeah, that's true. Like a chunk of gold is solid, so that's possible. A solution of gases. Is that possible? If you have more than one gas put together, it's always going to form a solution every time. So definitely C is correct. A mixture of solids. Oh yeah, you can get a mixture of solids. You could have a jar of jelly beans. That's a mixture of solids. Or you could have an alloy of zinc and nickel. Makes brass. That's a mixture of solids. It's actually a homogeneous mixture. A heterogeneous compound. That does not work. If you have a compound and you've said nothing else about it, it's just the compound is pure by definition. So you can't have a heterogeneous compound because a compound has a uniform number, it's uniform by mass, and I explained this in chapter 3. You have to take a look at that video because we didn't have that in class. but I posted it. A compound is pure, and the percentage by mass of the elements in a compound are always the same, no matter where the compound comes from. That's the law of definite proportions. Okay? So E is false. We really couldn't say even a homogeneous compound, because homogeneous and heterogeneous imply mixtures, and compound's not a mixture. But that would have been too sneaky if I had said homogeneous compound. Then it might have led you astray in the wrong direction. And heterogeneous is easier to justify. Okay, 119. 119 refers to this burette on the right. You can't see all of it, but the burette is a device that allows you to deliver a measured amount of liquid. That's why it's calibrated from 0 at the top to a larger number at the bottom, in this case 50. And this is in milliliters. So when you read a burette, you have to read it from top to bottom, not like a graduated cylinder from bottom to top. Okay, that's the first mistake you need to avoid. So if you find that the level of the liquid is down here and we started at 20, it's going to be greater than 20 is how much was delivered. If you started at 0, then it would deliver, looks like 22.0. So let's see, 119, was that it? Yeah, 119. Using 0 as your reference point, okay, so we're starting at 0. How much liquid has left the burette? How much has been dispensed? Use the correct number of significant figures, okay? So if we read 20 and we look at the subdivisions, between 20 and 30, there are 10 markings. So each one is worth 1, right? We subdivide between 20 and 30 is 10 milliliters. Each marking then would be 1 milliliter. We've moved down to this 22. There's 1, 2. It's not 3, it's not 1, it's 22. Then our answer would be, we're on the marking for 22. Remember that? So that is a certain number. 2 is a certain number for this measurement. The last number is a guess. So if we think we're sitting right on 2, then the last number is our guess, 22.0. That's why the answer is D and not E. Okay? I just want to drive that point home. Okay, 119, let's see. 124 is our next candidate. 124. Aluminum has a density of 2.7 grams per cubic centimeter. Is that going to float or sink in water? It's going to sink, right? Greater density. Water is 1.0. So that chunk of aluminum is going to sink. So if we need to find the volume of the aluminum, we just drop it in water, measure before and after, and find the difference by displacement. What's the mass of a rectangular block of aluminum? Measuring 11 centimeters by 22 by 34.5 centimeters. Okay, in this case, we don't do by displacement. We have a regular solid. So we need height, width, depth. Multiply the 3 together and you get cubic centimeters. So that's how you determine the mass of this block. So what's the question? What's the mass? We have density. We can calculate volume. So there's your mass. So mass then is equal to density times volume. Okay? So we got mass. No, we don't have mass, excuse me. We have volume and we have density. 2.70 grams per cubic centimeter. Times volume. So we have 11.1 times 22.2 times 34.5. And this is going to be cubic centimeters because we multiplied centimeters times centimeters times centimeters. And remember, in the sciences, you multiply numbers, you divide numbers, you add, subtract numbers. You also operate on the units of measure. So centimeters for this, multiplied gives you centimeters cubed. So whatever this value is, times this value, and notice, this is all multiply. So 3 significant, 3 significant, 3 significant, well, that's an exact number, so it doesn't count. But the answer will have 3 significant figures in it. So if we multiply those out and apply our significant figure rule, we should get 23.0, excuse me. There's a twist. Our answer is going to be in grams, right? Let's do the calculation then. That's grams, so the answer is going to be in grams first. But the selections are all in kilograms, correct? So let's say 11.1, 22.2, and 34.5, now times 2.70. And we can keep 3 significant figures out of this number. Okay, that's what my calculator told me. We can only keep 3, right? So we're stuck right here. 5 is greater than, well, 5 and greater means 9 has to be rounded up to 10. So that means it's 0, carry the 1. There we go. But our answers are in kilograms, right? So what is this in kilograms? Well, 1,000 grams is a kilogram. So if we change the units to kilo, we take this much, let's write it up here. We take 10 to the third out of that. Right? And that becomes kilograms. Right? 10 to the third grams. So now we have 2.30 times 10 to the first power. Is that one of your answers? No. But look, this is suspicious. 230 in standard notation. So let's see, what is that in standard notation? Well, that's 10. So 10 times 2.3 is 23, right? So we just move the decimal over here, and we have 23.0 kilograms. Is that one of them? Yep. A is the answer. Like I said before, these problems are designed to confuse unless you know what you're doing. I've heard instructors, administrators downplay the use of multiple choice as it's too simple. I mean, you can guess and get the right answer. Well, yeah, you could. But a well-designed multiple choice test is going to be very difficult to guess and get a passing grade. And they say, well, it doesn't lend itself to higher cognitive function. I tend to disagree. Simply because, just because it's multiple choice doesn't mean that you don't have to work the problem to get the answer. The higher level cognitive function occurs before you look for the answer in your selections. So multiple choice is perfectly valid exam form, besides the fact that it's easier to grade. But no one that doesn't know what they're doing is likely to get the right answer, especially if you have 5 choices. Right? If you only have 3 choices, yeah, your odds go up. Okay, 124, done. And 132 is the next one I'd like to stop at. Or as my English teacher would say, 132 is where I wish to, is the location at which I wish to stop. You don't leave your prepositions hanging out at the end of a sentence. Anyway, 132. Convert minus 47.9 degrees to centigrade. I keep saying that, Celsius. Used to be centigrade, then they changed Celsius, means the same thing, to Fahrenheit. And we did one of these earlier, right? You just plug the value in the formula and solve for it, right? So I think we probably should just skip this one. What you have to do is don't throw that negative out. Don't ignore that negative sign. That makes a difference. You get a different answer if it's a positive 47 than you do if it's a negative 47. What do we know from the lecture about minus 40 degree region? The value for minus 40, actually the values minus 40 Celsius is equal to minus 40 Fahrenheit. We determined that. I showed you that in my PowerPoints. So we should probably expect minus something in that region for Fahrenheit, right? But we have a couple of selections, 54 and 58, right? So they're too close together. You need to do the calculation to tell which one's right. But we know it's going to either be A or E, and in fact, it's E. Okay, so let's, oh, we got 3 in a row. 133, which of the following involves no chemical change, right? So what are our choices? Chemical or physical change? So if it's no chemical change, that means it's a physical change, right? That's the only choice you have. Baking a cake, that's definitely a chemical change, right? Because most cakes have what in them? Baking soda, baking powder, which converts to gas when you heat it up, and that's what makes the cake fluffy, makes it rise. That's what makes quick bread rise, like biscuits will rise because of baking powder, and it undergoes a chemical change to produce a gas. In fact, the gas is carbon dioxide. Boiling water, that's a physical change, right? And we don't have any other options here that would interfere with that one. So once we find, we don't have anything that says 2 of the above or 3 of the above. It only says which of the following involves the chemical change. Test-taking technique. In this case, the first one you come to that's right is the answer. That's B. We can look at the others. Light a match, burn paper, drive a car. All involve chemical changes. Okay, 134 is next. Okay, copper has a density of 8.96 grams per cubic centimeter. All right, it's going to sink in water. If a cylinder of copper weighing 34.94 grams is dropped into a graduated cylinder containing 20 milliliters of water, what will be the new level of water? Haha. Now you have to stop and think. So let's pull out the information that's given. So the density of copper is 8.96 grams per cubic centimeter. And the volume we're dealing with is milliliters, right? So what does that mean? Well, that also means per milliliter of copper, right? They're equivalent. So we can save ourselves a step right there. What else are we given? The copper has a mass of 34.94 grams. Now notice the wording in this problem. If a cylinder of copper weighing 34.94 grams, weight is a force, right? It's not a mass. So this is kind of this is the term weighing, giving you a mass, is grandfathered in from ancient times. When we say weight, we really mean mass. And many authors and instructors will say, if a cylinder of copper massing 34.94 grams, and I guess that's proper. You have to invent a new word because mass is a noun. And when you say, I massed something, or I am going to mass something, you have to convert that noun into a verb. And historically, mass has never been a verb, right? So that's a change that science has imposed. Some scientists have imposed upon the language. Just understand that when you see weigh, that if it's in the metric system, we're talking about mass. So 34.94 grams is the mass of this piece of copper, and it goes into a cylinder containing 20 milliliters of water. What will be the new level? All right, so we have a graduated cylinder. And we start off at 20. Okay. Actually, 4 significant figures. There we go. So, what's going to happen when we drop the copper in there? A cylinder of copper. The level's going to come up somewhere, right? And that's the value we want. So how do we get there? Well, we have to add the displacement to 20, right, to get that value. And where do we get the value for the displacement? The volume of the copper. So what we need is to solve that for volume, right? That comes over here, that goes over there. So we get this. So this is the difference. That's equal to the V here. So we have mass divided by 8.96 grams per milliliter, right? We check our units. Grams cancel. Milliliters is in the denominator of the denominator. It flips up. So we got the right units. We divide this into that. And let me go ahead and do that. 8.96 divide 3.89955. Milliliters. Okay. So, we've got 4 significant figures here. We can keep 4 down here. Right? So we have there. So this is 5. That means this has to be rounded up to 10. Carry the 1, 10. Carry the 1, 9. So there, we have 3.9 milliliters that can be added to this one. So we say 20 and 23.900. We can only keep this many, so it should be 23.90 milliliters. That's D. Okay? All right. So that was 134. 137. Let's see. I'm getting there. I think I got enough time to finish the ones I marked. And then if we have any time left over, we can go back and see if there are any other interesting ones. How many significant figures are in the number here? I won't even have to put this one on the board. 137. When you have a number that's written in scientific notation, the number of significant figures can be determined from the coefficient. So 4.00700 times 10 to the 13th. It doesn't matter what 10 to the 13th is. It could have been 10 to the minus 13th. And it would still be the same number of significant figures. 1, 2, 3, 4, 5, 6. 6 significant figures. Right. So that's, you can do that one in 5 seconds. Okay, 138. Let's see what 138 has to offer. Which one of these is not a step in the scientific method? Okay, you've got to think about what is the scientific method. We usually have 138. We usually start with an observation. And then we formulate an explanation for the observation. Actually, that might not be a good word. Yeah, as long as we understand that the explanation is not necessarily why. It just could be how it happens. So then we have what's a proposed explanation, which is a hypothesis. It could be as simple as this, then that. So if you set up an experiment with these conditions, then you expect to get these results. That's what a hypothesis means. Let's see. Then you have your hypothesis, and then you need to conduct the experiment to test it. Okay, and then you get some results. And then you see, do these results support your hypothesis, or do you need to change the hypothesis and try it again? In which case you go back, change your hypothesis, and you keep going in that circle. So let's see, what do we have to choose from here? Which of the following is not a step? Change the results to agree with your hypothesis. That's funny. Actually, it's so funny it makes me cry, because I know scientists that have done that. I mean, they don't change them a lot, but they use subtle techniques to modify the results to suit their hypothesis. One of the easiest ways is if you have information that's given, say, data, right? Numbers and units. You can look at that, and if the statistical analysis does not support your hypothesis, what you may do is go in and say, that's an outlier. Throw that one out. Throw that one out. Throw that one out. Now reanalyze it. Okay, now it agrees with my hypothesis. So the temptation to falsify your data is very strong, and something that we have to guard against as scientists. But A is definitely wrong. The rest of them, develop a theory or a model. Well, yeah, if you have enough experiments, you can keep going right? And make a theory out of it. That's true. Perform an experiment, yes. Observation, yes. Hypothesis, yes. Those are all parts of the scientific method. The scientific method is really a roadmap to arriving at a justifiable answer to a problem. And changing your results to suit the hypothesis is not one of them. Okay, what's next? 148. Let's see what 148 has to say. There we go. An example of a mixture. Now I'm getting these, okay, that's all right. We'll say, what's a mixture? Well, if you've got a pure substance, you don't have a mixture, right? So we can eliminate, process of elimination, take out the pure substances first. Example of a mixture. If it says all of these, then all we have to do is find one pure substance and E is false. So the first one is gold. That's a pure substance. It's not a mixture. E can't be right either. So now we're left with B, C, and D. Air in this room, that's a mixture. Purified water, nope, that's a pure substance of a compound. Hydrogen fluoride, that's the name of a compound that implies a pure substance, right? So the only mixture is the air in this room. And in fact, it's a homogeneous mixture. It is a solution. So that's why B is the answer to this one. Okay, let's go to 149. How many of these are compounds? What is the definition of a compound? Well, a compound is an association of some form, a bonding of two different elements or more. Right? So an example of not a compound would be one of your diatomic elements, right? And those are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those would be not compounds because they're the same element, they're just tied together. Now, if we took one of these and combined it with the other one, yeah, that would be a compound. Say, put these two together. Hydrogen chloride, or if you put it in water, it's hydrochloric acid. That's a compound. It's got two different elements. So let's look at our examples. Water is a compound. Dinitrogen tetroxide is a compound. Sodium hydroxide, that's a compound. Manganese dioxide, actually that's the proper name is manganese 4. I'll explain that in the subsequent chapters. Manganese 4 oxide and hydrogen fluoride. Those are all compounds. They're formulas for combinations of two or more different elements, right? So 1, 2, 3, 4, 5, there are 5 of them. That's why A is the answer. How about 150? How many of the following are pure compounds? Okay, so test taking technique. Compound, you eliminate elements, even the diatomic elements. Sodium is an element, right? You know that one because you've memorized the symbol. Now there's no S in that because why? Because sodium is derived from the Latin natrum, which is for sodium. Sugar. Sugar is a compound. And if sugar is the name, that's all there is, that's a pure compound. Oxygen, that's not a compound. It's a diatomic element. Air. Air is not a pure compound, it's a mixture. In fact, it's a mixture of diatomic elements and some compounds. Right? Nitrogen and oxygen predominantly, but there's also some carbon dioxide, which is a compound. There's usually a little bit of methane, and there's probably some fluorohydrocarbons from exhausted refrigeration units. Air, that's a mixture. It's not a pure compound. Oh, we already did that one, didn't we? Sorry. Iron. Iron is a pure, it's an element. Right? Fe for iron. You'll probably guessed by now, that's from the Latin too. Ferrum. Ferrum means iron. So that's an element. So how many of the following are pure compounds? There's only one. Sugar. That's why B is the answer. Okay, let's see how we're doing. We got 40 minutes left. We're doing pretty good. Stop me if you have questions or comments. Assuming you're still there. I see names, but I don't see any pictures. 154. Okay. I know some instructors, they set up little quizzes. You may have had some instructors like that. Quizzes that they give you periodically during the Zoom session to be sure you're still there. But that takes away time from review, and I'm recording it anyway, so I'm not as concerned. Except that I'm giving you credit for showing up, so I need to at least see you once, know that you're supposed to be there. But I'm from the old school, where you go into a classroom, a chemistry class, and there are 100, 150 students in the auditorium for that one class. I mean, is the instructor going to take roll? No, he's going to give you exams, right? If you show up and you pay attention, you should pass the exams. If you decide not to show up and skip class, then you're probably going to fail, and he doesn't care anyway. You've already paid your money. His salary is good. It's your problem. That's the old school. Okay, 154. Helium. Oh, what has changed in the interim? Now government's involved. Government's putting money into these institutions, and they want to know that the students are there. That's the primary reason for taking roll, is to satisfy financial aid. Okay, 154. Helium is an example of what? Well, light bulb should go on, right? That's one of the elements you had to memorize, helium, He. So you know it's an element. So all you have to do is just find the one that satisfies. There's an element. You're done. 5 seconds. 156. Which of the following of these is an element? Well, we look. Water's a compound. Earth is definitely a heterogeneous mixture. Salt is a compound. Brass is a solution of two metals, usually copper and nickel. Oxygen is the only element in there. And as it turns out, it's a diatomic element. Okay, let's see. 161 is the next one I'm interested in. Down one more. There we go. What's the result of the following multiplication expressed in scientific notation to the correct number of significant figures? Okay, here we go. 161. This deserves some comment. So this is a simple calculation, but you've got to be sure that your significant figures are correct and actually do the calculation. 5.46 times 10 to the third. And 8.0 times 10 to the minus third. All right, to the correct significant figures. All right, when you're operating with scientific notation, you multiply, in this case, the coefficients first, and you get a number. And then you operate the powers of 10, and you get an exponent, powers of 10, multiplied by it. So if we do that, 5.46 times 8.0, is that right? Yep. Is 4.368. No, 40.368. Right? 8 times 5 is 40. But we haven't resolved those significant figures yet. Right? We're going to keep that for the time being and do the exponents. So when you multiply numbers that are the same base unit, in this case 10, you add the coefficients. So 10, 3 minus 3, right? Plus 3 and minus 3 yields 10 to the 0, which is what? 1. So 1 times that is all there is left. Now we need to resolve this, right? There's 3 significant figures, there's 2. So we can only keep 2 in our answer because this is rules for multiply. So 2 is this, and 3 is less than 5, so it goes away, and we keep 40. Well, the answer is in scientific notation, right? So we say, move the decimal place over 1. There, 4.0. Wait a minute, did I do that calculation wrong? Or maybe the answer's wrong. The possible answers. Let me do it again. 5.46 and 8.0. I did it wrong. It's 43.68. Now we can keep 2 here. So that's 6. That makes this one 44 times 1. So now we move it over 1 place. There we go. 4.4 times 10 to the first power. That's why C is the answer. Okay? All right. Let's see what else we got here. 169. Let's do 169. Scroll down. There we go. All right. So this is fill in the blank from one of these possible selections, A through E. A blank change involves a change in the fundamental components of a substance. A given substance changes into a different substance or substances. So we're talking about identity change. And what does that require? Well, it's either physical or chemical. And you can tell by the wording a change in the fundamental components, right? So all these others are thrown in there to confuse, which makes sense. A kinetic change? No, a kinetic change is just a change of motion, speed. Potential? No, we're still talking about energy, and that's not what we're talking about. It's a fundamental characteristic of the object. So it's either physical or chemical. And in this case, we know it's chemical. Okay, 169. Okay, so that's all the ones that I had selected. And we can look at, I can see if there are any others that could possibly be useful. Let's see. How about this one? I don't even know the number. Let's see if I can find it. Then you can reference. It's good to know the number so you can reference it. Number 9. We'll go back to number 9. There we go. Here we need to, excuse me. Here we need to differentiate among these different statements which describes a chemical property of gold. Remember in the lecture, I tried to differentiate between properties and changes. Property refers primarily, a good way of thinking of it is potential. What is the chemical potential of gold? Well, in order to be a property, we have to eliminate anything referencing change. That's not considered an expression of potential. So gold is very dense. That's a property, right? But it has nothing to do with the chemistry of gold. It's a physical property, right? So A can't be hit. Gold is a soft metal. That's a physical description. Gold is malleable. So B can't be it. Gold is an inert, unreactive, or non-reactive metal. Now we're talking about the potential for reaction. Right? Even though gold doesn't react, we are talking about the chemistry of gold. It is non-reactive. So that is a chemical property of gold. Right? So since we don't have any oddballs at the end, like all of these, none of these, 2 of these, then once you find the right answer, you're done. But if we look at gold as a yellow metal, yellow is a physical property. Gold is a good conductor of heat and electricity. That's a physical property. They're all properties here, but this is the only one that is the chemical property. Okay? All right. So let me see. I'm going to look for another one. And if anyone is bothering you guys, just sound off. How about this one? Let's see. This is a simple unit. Well, on the surface, it seems simple. But it brings out a very important point that I need to make and neglected to mark this one off as potential. So I just need to find it in your review document so you'll be able to reference it anytime you feel like. Probably at the back, and I started at the wrong end, right? If I can't find it easily, I'll just go ahead and put it on the board, talk about it. Here we go. 172. Almost at the bottom. Here it is. Okay. It's a conversion, and we want to convert 5.39 meters per second. So it's a velocity, displacement, meters, time, seconds, meters per second. This happens. We want to convert it to kilometers per hour. Okay. So how do you do that? When you're doing dimensional analysis and you're converting a number that has more than one unit of measure involved, do one unit at a time. Convert the meters first, then convert the seconds. As one example. Or you can convert the seconds first and meters second. It doesn't matter, as long as you do it correctly. So we're going to take the meters first. So how do we convert meters to kilometers? Well, we need kilometers in the numerator. That's pretty sorry, kilometer. There we go. Convert kilometers, so it needs to be in the numerator. And we need to cancel meters. Okay? So we need an equivalence. How many meters are in a kilometer? Well, kilo means 1,000. So we need 1,000 meters for the kilometer to be the same size unit. 10 to the third. Okay? So there's meters converted to kilometers. We're done. Halfway. Now we need to convert seconds to hours. Right? So if you don't know the direct conversion from seconds to hours, you got to do it stepwise. We know, we have to cancel seconds. It's in the denominator, so it needs to be in the numerator here. And we need minutes here, because I know that 60 seconds are in a minute. Right? So we got seconds done. Now we need to convert minutes to hours. So minutes needs to be on top and hours on the bottom. 60 minutes, and 1 hour. There we go. Now we got both units converted. We did meters first, then we did seconds, and hours is on the bottom, kilometers is on the top, and everything else cancels. We're good to go. We've done all the thinking. Now we just need to crunch the numbers. And it should be, and take into account 3 significant figures. These are all exact numbers, right? So 3 significant figures will give you 19.4 kilometers per hour. Okay? Well, the proper abbreviation for hour is H. Out of force of habit, I write HR. We've got about 20 minutes left. Let's see if I can find anything else. Or if you have thought of a problem, just sound off. Let's see. We may have covered everything of importance already. I think we have. Yeah, I think we have. I think we're good to go. If you understand everything that we've done today, and you can go away, say eat lunch or take a nap, and then come back and work all those problems from memory, then you should be fine for the exam. Now, I assume everybody has got Respondus Monitor Lockdown Browser on your computer, and you're ready to go, and you've done the practice test, and you know that your technology works. If you haven't, you need to do that before the exam comes, which will be on Tuesday. You can take it before then, right? There's no law against that. Since it's on Blackboard, and all you need is to just go in there when you're ready and take the exam. But the latest you can take it is Tuesday before midnight. Okay, and on Tuesday, what we're going to do is we're going to come to class, and I'm going to hop on chapter 4 and take off. So we're not going to stop and do exams or anything like that. Not in this environment. Of course, if we were face-to-face in the classroom, we'd have to take class time out to do the exam. Well, actually, you know, I could administer the exam in Blackboard even if we were face-to-face. That would give us more class time. But historically speaking, I've always done it face-to-face so that you can work the exam on paper, hand it to me, and I can grade it before you leave class. You'll have the grade before you go home. I like to get grades back as fast as possible so that you can see where the mistakes are, if there are any, correct the mistakes, because chemistry is an additive science, like most sciences. You start off with here, and then you use what you learned here to learn something new and develop new skills. You got to have these nailed down. That's why I started off with memorize the periodic table, right? Those elements that I showed you, you need to have those memorized. Otherwise, the next chapters are going to be a nightmare. You're going to be learning while you're learning the elements while you're trying to use them. So let me stop the share, see if there's any observations or questions, whatever the case may be.